Okay, sorry about the delay. Just come back here. Okay, let me get started now. The first question is let me put this on. Sorry. I guess first question is: are there any questions? Um, as far as projects go, the what you call it? I posted on my webpage two examples of good final reports in the past. So if you want to do, use those as models, I think that's good. The page limits, again, I talked with the TAs a lot about this. The page limits for the final report are going to be 8 pages plus references. So you're going to have a page with references on it. But a strict limit of 8 pages of content. I guess on the Piazza, they posted a format that is double column that lets you fit a little more stuff into it. But I don't want to see more than 8 sheets of paper plus references. Any questions about the project? Okay. Um, okay, so what I'd like to talk about today is I'd like to talk about machine learning. I know many of you thought that this was going to be a course on machine learning at the beginning. But obviously, we spent most of the semester talking about, what I will still call important data science prep things. Okay, because I still think that generally speaking, the features are more important than the algorithms here, and the thinking about your data set is more important than your algorithms. But obviously, if you're going to be trying to build a model, machine learning is a good way to build models. And there are a lot of different uh, machine learning algorithms out there. Everyone in here should have used linear regression. Everyone here probably has played around a little with a few other methods. Um, you know, the when I think about comparing different machine learning algorithms, I find that it's easy to take your data set and run it through a bunch of different machine learning algorithms and have it come up with a model and have it you score the models perhaps with some test set. But you know I'd like to spend a little time trying to look at why there are different machine learning algorithms. What makes one of them different than the other? What makes one of them maybe a little bit better than the other? And if we think about the dimensions on which we might care about machine learning algorithms, one is a question of what I'm going to call, power and expressibility. How good is the machine algorithm? How good are the models at the end of the process? Um, that's important, but we might care about interpretability. If I look at a model, can I understand what it's doing? This is important in many contexts. You know, if, if you're trying to understand your data set, an interpretable model that's not as quite, it's a little bit lower performance than a uninterpretable model may tell you a lot more about your data set, and stuff like that. There's some question of ease of use. Certain methods will work, out of the box for just about everybody. And other ones require a bit of a wizard to get good results on it. Um, there's also the issue of training speed. We saw that, many people again are interested in deep learning. Deep learning models historically require heroic efforts to train. There are people who worry about the energy usage of computers that are training deep learning models, that this is going to cause global warming because of all the energy this thing uses. And there's a separate condition of prediction speed. Generally, as engineers, we worry more about, I guess, the training speed because that's what we're sitting there and watching it while it's training. But if you have a model that's being deployed, there's an issue of, how fast is it making inferences? Okay, and that's actually a different, performance issue than training speed. So when I wrote the book, I tried to I went and consulted a bunch of people who I thought were knowledgeable on machine learning. And I had them rank each of the, let's say, basic methods, the methods that we would be discussing in a course like this, okay, in terms of these different properties, okay? And, bigger numbers are better, okay? And again, we've seen a couple of methods so far. We saw linear regression and nearest neighbor methods. Um, you know, how expressive are they? Well, by adding the appropriate features to a linear regression model, you can make it nonlinear. Okay, nearest neighbor methods are nonlinear. You can create pretty powerful, pretty good models there. Both of them have the property that they're relatively explainable. If we look at ease of use, I trusted everybody here to build a linear regression model without really talking about it. And generally speaking, people were able to succeed at that quite well. Nearest neighbor models, you have to worry about distance functions, you have to worry about some other things. Still, what's good about nearest neighbor models? They take no time to train. So that's certainly about as good as you can do on the training speed objective. Linear regression is generally quite fast, okay, for the kind of data sets people tend to use. When it comes to predictions, linear models tend to be quite quick to evaluate, just basically evaluating a polynomial. Whereas nearest neighbors requires searching through all the data sets. So if we take a look at it, nearest neighbor methods are bad because of the runtime. If we look at this thing, linear regression is good on just about everything, except, the models are, linear, okay? The models, you can build often better models, okay, if you really work at it. And so what I'd like to do for the rest of this for the next week or so, is talk about the different kinds of models and how they compare. We'll talk about decision trees today. Decision trees have the property that you can build probably more expressive and more powerful models than with either of the methods we've talked about so far. And generally they're good on the other dimensions. Okay? We may talk about boosting. Boosting is a way that's going to be talking about that can build even potentially more complicated models. Okay? That again is harder to get right. That's kind of, I guess, a way to think about it. Slower and stuff like that. Deep learning, which is everybody's favorite thing these days. In terms of power and expression, you have millions and billions of parameters there. Okay, you can build very expressive models. Generally speaking, it requires considerable skill to do it right. It takes a long time to train. They're not as fast at inference time, and you don't know what they're doing. So there's a kind of a trade-off between these methods. Any questions about the general positioning of machine learning methods in where they sit? There's a famous statement which people call the no free lunch theorem. Okay, that is kind of an argument that there is no single machine learning algorithm that will work best for all in all cases. Okay, that on certain data, for every problem you have, On certain kind of data sets, one method is going to beat the other. Generally speaking, again, the lessons that I come away from that table with is that linear logistic regression is not bad. Okay, and the comparative advantages of many other methods are kind of murky. Okay, but still, a lot of these learning algorithms are quite clever, and I think it's interesting to go through them. Any questions? So what I'd like to talk about today is a method, decision trees, that is kind of optimal for cases when linear classifiers are really bad. Okay? You could imagine a world where, let's say that we had, two features, X and Y, and two classes, blue and brown. Okay? As in this particular figure over here. In this particular example, the regions are kind of defined by what we would call an exclusive OR function. Remember what the exclusive OR function was? In the XOR, okay, if we have a logical exclusive OR, okay, the OR function, let's remember, we had a table of, X and Y, and we computed the OR of these things. I guess this is what the truth table would look like. For the OR, okay, it would be a 1 whenever we had at least one of the two things was 1. An exclusive OR would be, we would have a 1 when only one of the things were 1. So this would be a 0, 1, 1, 0. Okay? And again, if we take a look at this one, if Y is 0 and X is 0, brown is defined whenever either X is high or Y is high, but both of them are not high. Does everybody kind of get that? Now you can imagine, again, exclusive OR is a pretty simple function, okay? You could very well imagine classes in the world that are defined, have an exclusive OR type behavior. It should be clear that if you tried to solve this with a linear classifier, you would fail. There is no way to draw one line to separate the browns from the blues. Does everybody kind of see that? Okay, so this is an example where linear classifiers will do a bad job. How would nearest neighbor do on this data? If we had a function like this, how would a nearest neighbor classifier do on this kind of data? Yeah. Any sense? Good, bad? Someone? I think nearest neighbor would do quite well here, right? Because, again, if we think about it, if we think of these, if let's say all the points are appropriately labeled, okay, in this particular case, all this region is going to be brown, okay? If this point is brown, all of this region is going to be brown, okay? And if this point is brown, all that region is going to be brown, right? So nearest neighbors, actually, methods would do just fine on the exclusive OR, assuming you have sampled this space, sufficiently well. But let me show you another method that can do very well on a space like that, and that's a decision tree. A decision tree is kind of a hierarchical sequence of tests, okay? And that it's a tree, a rooted tree, so it starts from a root. And inside every node is a test, okay? A test of one variable, a relatively simple test. The first test here on this decision tree is x greater than 0. If x is greater than 0, we're talking about the region on this side. Okay? If the region is on this side, again, if you look at this particular picture, again, this is exclusive OR data. Remember, we got blue here, red here, red here. The shading don't get fooled by the shading of the light blue to the brown. That's the best logistic regression line that was found for this particular data. And obviously it does a terrible job. But as far as a decision tree, if we look at the first test, is x greater than 0? That means we are now interested on this side in the space over here, and on this side in the space over here. If we're only interested in the space here now, the test of is y greater than 0. If y is greater than 0, then we get this region and everything is red. If y is less than this region, than 0, we're in this blue region and everything is blue. Okay? And again, the same thing can be done on the other side. It happens that the tests at the second level were the same. Okay? But there's no reason why that had to be. Okay? If, on the other hand, x was less than 0, if y is greater than 0, we're in class blue. Otherwise, we're in class red. Okay? Any questions about that? Any questions of what a decision tree is or how we make such decisions? Yes?
Can we have some probability in each edge?
So can you have a probability in each edge? Well, okay, so in practice, it should be clear that when you have a test, there's no reason why it's equally likely to pass through each test. Okay? So let's say I did a test here and said anybody who's less than 7 feet, okay, I'm gonna give it, I'm gonna do something too. But if they're taller than 7 feet, I'm gonna do something else too. Now that split is not going to happen in equally likely according to the population. In fact, it's segregating, NBA level tall people from the rest of the world. Okay? So there is no implicit notion that the splits have to divide the population equally. And that would give you a, So you might think of there as being an implicit, notion of probability at each test. But there's nothing explicit here, okay? Any more discussion about that?
I remember that we use something, a structure like this for calculating the probability of some chain rule for independent
Okay,
events.
what you could imagine is that one thing that is true, that there's different ways, right now on the tree itself that I'm looking at, no probabilities. What could be true is that what that relative the classes involved. And when we look at how you train one of these trees, there are things that look like probabilities. The probabilities tend to be on the nodes at the end. Okay, so if I was going to say where are their probabilities, in this case I am making in the way I have, in the simple tree that I have built, I have said that any leaf is going to be a label. This is class 1 if you're in x greater than 0 and y is greater than 0. Now you could imagine if there were some blue points here in that region, the probability of being in class 1 really shouldn't be 100%. It shouldn't be 100% true that you're in a class 1. It's enriched for class 1. You could imagine that instead of having the the label as an explicit discrete label, I might tell you in this region that you have a 0.97 chance of being in class 1 and a 0.03 chance of being in class 2. So having probabilities associated with the leaves makes sense. Probabilities associated with the edges to me don't make sense, because let's say at this point, we know very, the probabilities associated, well, let's just think about that actually. The probabilities associated with the edges don't make as much sense to me. Although you could imagine it be the sum, the edge probabilities could be some kind of a weighted sum of all the elements below it. Okay? And in this case, what would you have? In this case, it would be 0.5 class 1, 0.5 class 2, 0.5 class 1, 0.5 class 2. So you could interpret these edges as having probabilities. But I think that the proper interpretation here is based on the class divisions in the subtree below it. Okay? Any questions? Yes.
So is this only used for classification?
Is this only used for classification? Well, could you use something like this for regression? Well, what you do know here, let's say that each one of these elements had some kind of a, of a numerical value instead of a label. If we know that this is a region now which is relatively pure, the items look very similar, then there's no reason why you might not do a regression thing here. You might, for example, instead of the interesting property might not be the label, the interesting property might be the average of the values. Let's say we were interested in the lifespan of people, how long they were going to live. If we find ways of partitioning these trees so that similar people are going to, kind of fall in similar classes at the end, certainly you could take a, let's say, an average of the target value as a prediction for the numerical thing. That's regression. Or maybe now that you've got a homogeneous class of people, maybe you would build a separate regression model down there and get a finer estimate. Okay? So one way to think about it is that the decision trees kind of provide some kind of a implicit clustering of the points, and then you can do anything you want with those clusters. Any questions? Those are nice questions. I like having questions. Okay, so how did a decision tree work? Again, every instance is going to ultimately end up at a leaf. Okay? The path from the root to the leaf describes what did it, how you went around and did that classification. This is a a tree that was built from data on the Titanic to decide whether or not you survived. Okay, if you were on the Titanic. What was the situation? If you were a male, you know what happened to Leonardo DiCaprio? Male didn't make it, right? If you saw the movie, it was women and children first, right? According to this, we would say that if you were a man, it was all over, okay? Actually, if you were to take it back, if you were female, okay, you survived. According to this, 73% of the women survived, okay? And that represented 36% of all the nodes. If you were a male, what happened was this test. It's now going to say, were you older than 9.5 years? Remember, the saying was women and children first on the lifeboats, right? If you were older than this, you weren't let on the boat. So a man who was older, who was 10 years old or older, okay, 61% of them died, and that represented what you call it, 17% of the people, okay, on the Titanic. Now, what if you were a male and, younger than 9.5? It turned out it made a big difference whether or not you had brothers and sisters, okay? To get on a lifeboat, you needed to have your brothers and sisters pushing you onto the lifeboat. If you had a lot of children, okay, actually, no, I take it back. It looks like it's the opposite way around. If the number of children siblings is high, probably to have a large number of brothers and sisters on the Titanic, probably that meant you were a poor family and steward. And only 5% of those people survived. Okay, but if you had relatively few brothers, 89% of them survived. Okay, so what's the important thing on a tree like this? The goal is to use this tree so that we partition the leaves, so the leaves are relatively pure composition. Ideally, you want in the leaves either most of the people to survive, or an overwhelming majority to survive, or an overwhelming majority to die. And that then makes the classification decision easy. Okay? Any question about that? Okay? So this is the idea of one of these decision trees. Okay? And it's also a good example that the decision tree is interpretable. I can read this decision tree. I know what the features are at each node. Okay? And I can kind of read what happened. And it does a reasonably good job of doing that classification. Any questions? No, okay, that I don't want to talk about. So what are the good things about decision trees? One good thing is that they permit very complicated decision boundaries. Okay? This decision notion of chopping it off, saying, is it greater than this? Is it less than this? Is it greater than this? Is carving out a special region that you can't carve off with one line. Okay? So decision trees can be expressive. Decision trees can work very naturally with categorical variables. If I wanted to make a decision, okay, did the person have red hair? That's a perfectly fine test to have in a node. It doesn't have to be a numerical thing. I could say, is the person red-haired or bald? That's a perfectly valid kind of a test. Okay? We've seen that they're interpretable. We can read them. We could do regression within a leaf subset. That was the earlier question here. Okay? We can make them robust, as we will see, by making multiple decision trees and voting. Okay, that's what we'll talk about in the near future. In general, decision trees work quite well. One of the biggest disadvantages of them is that they are kind of hacky kinds of things as opposed to elegant math-like things. Linear regression has a great theory. Nearest neighbors is kind of involves all of geometry. Support vector machines, there's a very much of a geometry and an optimization flavor for it. So decision trees tend to work quite well, although they are somewhat, I will say, ungainly compared to the other, algorithm methods. This maybe doesn't scare us, but it's kind of at least one thing that I think of when I think about decision trees. Any questions? So how do we build decision trees? Okay, generally speaking, the way that you build a decision tree is from the top down. You have a universe of all your elements here. Let's say that there are two classes. You've got positive and negative things. Okay? Ideally, we now want to try to find a test with the property that after we have done this test, the purity of each node in terms of classes has changed, okay? In the ideal case, what would we want to have happen? We would want it to be that if we start out with an equal number of pluses and minuses, we would like our Rooten test to be enriched, where on the left side it's enriched in one class, perhaps positive. On the right side, it'll be enriched in, in some other class, okay? And then once we have it, we're now going to recur and split each sub-half, okay? Generally, each split we want, we're going to do in a way that is a simple test. We could build some complicated decision test using multiple features at each level. Generally, when people are building a decision tree, each node is going to be a simple test on one feature, usually just a threshold test. Is this feature greater than or less than the threshold? Okay? And, so basically one way to think about decision tree construction is at each node, we choose what feature we're going to want. Sorry about that. Choose what feature we want in here. Let's say feature X. And then we will identify what is the threshold that, given the examples, does the best job of partitioning. If you think about it, that's a lot like the kind of thing that we did with, when we were talking about area under an ROC curve. Okay? We had all of our examples scored according to the feature. And each feature, this is sort of our dimension X, okay? We had at every point, we could use that one feature as a classifier. If we set the threshold here, everything on this side was going to be positive. Nothing was classified positive. If we set the threshold here, not everything was classified positive. If we set the threshold over here, okay, these guys would be classified as positive, and these guys would be classified as negative. And this is a pretty good split. Okay, originally there were a roughly equal number of positive and negatives. If we set our threshold over here, this side is now 80% positive. This side is now 5/7, which is what? Probably about 65, 70% negative. This represented a good split. Any questions? Now, to make that algorithm precise, we have to look at what is the actual split criteria that we're going to be using. We've got two kinds of ideas that we would like to have happen. One is we might like a pure split. Suppose I drew, my split right over here. What would be good if I drew my feature split right over here? So on one side of this, I have two examples, both of which are positive. And on the other side, I've still got a little bit of a mess. The good thing about a split like that is that one of my sides is now completely pure. I know that if you fell less than this threshold, you were a positive example. Okay? What's the bad thing about this split, though? Say overtrain, you're saying you're not happy that this is a small number of things. It should be clear that if I want a split where one side is pure after every single test, if that was my criteria, could I do it? I could always do it, right? Here's another one. Here's a thing. Everything on this side is positive, okay? The good thing about that is that every node is going to be labeled exactly right eventually if I go down and do this for the entire tree. The bad thing is that it's going to be, potentially overfitting. It's relying, if I'm only picking off one or two elements and asking for a very pure split, okay, it's quite likely that my partitions are going to match my data so closely that I'm going to overtrain. What would be a good or bad about a split instead? Sorry about that. That happened in the middle. What would be good about a split that just split the thing in the middle? So I had actually half the elements on one side and half the elements on the other side. That would be what I would call a balanced split that caused equal-sized groups. What would be good about a balanced split? Okay. One thing that a balanced split does for me is it produces a very low height decision tree. Okay? Could I always find a split that puts half the elements on the left and half the elements on the right? Assuming the values are distinct, and the answer is yes. If so, what would be the height of my decision tree if I had n items at the beginning? To come up with a tree that was perfectly balanced. Log n, right? What would be the height of my decision tree if I insisted on picking off one element with each test? What would be the height of my decision tree? N, okay? So it should be clear I could, if I demand pure splits at each point, I am going to end up with a tree that might be of height n, okay, which is bad. On the other hand, it would make no mistakes on any of my examples, which is good. On the other hand, it's also violently overfit, so that it probably, when I gave it other examples that were not in my training set, it would probably do badly, right? What would be good about my balance split? I would have a height of length, a height of log n. The height, what is the advantage of it having a short height as opposed to a long height decision tree? The complexity when I query it, right? When I have a new element and I want to test it, okay? Then actually the time it's going to take to make a decision on the new element is proportional to the height of the tree, okay? If I even did perfect splitting, my leaves would eventually be pure, right? My leaves are not going to become pure early on. I'm not going to have leaves high in my tree. If I did a perfectly balanced split every time and went down to the leaves, okay, every leaf would be pure. This would be just as overfit as the pure split one, okay? I guess it's faster, but it'd be a faster, heavily overfit one. Any questions? We would still like our splits to be pure. We would like our splits to be balanced. Neither of these criteria by itself does exactly what we want, okay? So we would like to have some kind of metric that's going to kind of combine these two things to help make the decisions. So one way to think about decision trees, to think about them as what makes a good split, is to think in terms of information theoretic entropy. The entropy measures how much uncertainty we have as to, let's say what a label is. Suppose we have data that's in m different classes, okay? For a binary classifier, m equals 2, in general, we could imagine m different classes we're trying. No reason why a decision tree has to be limited to binary classification. We're going to make one decision at every leaf. There's no reason why we couldn't have a lot of different classes. Okay, but generally, let's consider binary classification. Okay, well, okay. The entropy of a set of things is going to be over every one of the m different classes, the frequency of how many times class I occurs times the log base 2 of how many times that class occurs. Okay? So let's imagine a world where we had n items, half of which were, half of that which were, okay, half of them are going to be, class 1, and half of them are going to be class 2. Okay? What is the amount of uncertainty here? Well, the frequency in class 1 is going to be 1/2. The frequency in, what's the log base 2 of a half? Minus what? -1. Okay? And we sum that up over the other one, that's also going to be -1/2. And then we negate the outside, so the minuses go away. Okay? The entropy, okay, of in this world is going to be 1. Okay? If I have a perfectly good so if I have two classes, n items and two classes, okay, if they are equally likely, my entropy is going to be 1. If, on the other hand, I have two classes, but all the items are in the same class, then what's going to happen? Two potential classes, but all the items in my sample belong to 1. What is the entropy going to be? 0, but why is it 0? It's 1 times the log base 2 of 1. What is the log base 2 of 1? 0. It would also be 0 times the log base 2 of 0. What is the log base 2 of 0? Minus something bad, right? Minus infinity. But 0 times anything is 0. So this gets blown away, this gets blown away. If the items in the class are all in the same, if you have two potential classes, but all the representatives are in one class, the entropy is 0. If you have two classes, and there are half of them the items are in one and half of the items are in another, the entropy is going to be 1. Okay? Generally speaking, if you have m classes equally represented, the entropy is going to be the log base 2 of the number of classes. So again, for us in general, for the binary case, it was the log base 2 of 2 or 1. Any questions about how to measure entropy? And entropy comes up in information theory. It's a measure of amount of uncertainty we know about something. If we know something belongs to this pool of items where all the items are black, we know that the item is black and there's no uncertainty. If half the items were white and half the items were black, we are uncertain as to maximally uncertain as to what color the item is. Okay, any questions? So a good criteria to try to split the nodes is what people call information gain. Okay, what is the idea of an information gain? We have a set of items right now, S. We want to do a test that's going to create a set of items, S1 and S2. Okay? We want, okay, as pure a division as we can on each one of them. Okay? So we want, actually, ideally, if it's a good test, it has reduced our uncertainty as to what the right label is. Entropy measured uncertainty. Information gain is what is the original information? What is the original uncertainty? Okay? Minus the uncertainty after the split. Okay? What's our uncertainty after the split? Well, there are two sides of the test. There is a side on the left and a side on the right. Each side is going to have a fraction of the elements. Okay? There's the size of S1 elements on the left side. There's the size of S2 elements on the right side. S1 and S2 adds up to the size of S at the beginning. This is the fraction of the elements on each side. And this is what the entropy is on each side. Okay? In our dream, what is going to happen? Originally, we have a lot of entropy. In an ideal world, what would have happened? The entropy on each side of it went down to zero. That's the best that could happen, right? So if the entropy on both sides went down to zero, then the information gain, it was the original entropy of the set. That's a big number, right? What if, on the other hand, the entropy, we didn't really make anything more pure? Let's say we had half white and half black, and after we did it, on each side, we have half white and half black, half white and half black, right? What's going to happen? Well, there's going to be half as much things on each side. The entropy is going to be the same on each side as it was originally. The sum means that the two halves, the total component, the entropy could remain unchanged. Okay? If when we did the split, basically it remained just as disordered on both sides, there was no information gain. Potentially, the information gain could be, ideally in a dream, as much as the full entropy of the original set. Okay? But in general, we can pick the split that maximizes the information gain. Any question about that? Okay? What is going to happen in the case where, let's say we had one positive, we found the split, and it separated off one positive compared to everybody else? Is that going to produce an information gain? And is it going to be a big or little information gain? On one side of the equation, namely, where did I draw that thing? Here, on this side of the cut, the entropy is going to go down to zero, which is great, right? The trouble is the weight of that is only going to be 1 over n, right? Only 1/n of the points are now going to have an information gain of zero. You have an entropy of zero. The other side is going to be n minus 1 over n. Okay, so almost all the points. And the entropy is going to be pretty much unchanged. Okay? So odds are you're not going to get a very big, information gain, splitting off a certain number, one or two elements in a pure thing. You get a lot of information gain, you want to take a healthy chunk of elements and and split them into enriched sides. Any questions? And again, there's other metrics that we can use, but the basic goal is we want as many of our elements, we want our nodes to be relatively pure, but we also want them to be relatively large, and the information gain criteria does a good job of capturing that. Any questions?
The index is I, right? Not K.
What?
The index is I, not K. Right?
The index here should use I, right? Okay, guilty. Someone mails me, I'll try to fix the slide. This should be the sum of all the classes, right? There's no J there. Any questions? Now, notice that this information gain criteria sounds good. Notice that it is not enough to produce a good decision tree, okay? Think back to our exclusive OR set. Remember the exclusive OR example that I gave you at the beginning? There existed a beautiful decision tree for it. I mean, this decision tree is as good as it gets, right? What happens after the first split? If I do my split like this, how much information gain did I get after the root split? Originally, the set was half blue and half red. What is going to happen after that first split? What's going to happen on the left? Half blue and half red. What's going to happen on the right? Half blue and half red. Does everybody see that this did not produce an information gain at all? Okay? If you're going to be building decision trees and trying to do a really good job, okay, you can't make it based just on local, this is an example that proves that local decisions are not really going to help you very much. It'd be, a local decision is not going to find this thing. What is probably the information gain criteria going to be looking at? Maybe they're going to find and say, well, if I go over here, let's look at it. Is there any place? It looks like if I did something like over here, it looks like there's a lot more red down here than blue. Okay? You could not find the right split by just looking locally. Ideally, if you're really going to build good decision trees, you should be doing a certain amount of look ahead. Explore for all possibilities, look at all possibilities afterwards. And hope that after a couple of these splits, the world will become clearer. Okay? In general, finding the best decision tree is an NP-complete problem. So you're not going to find the optimal decision tree by any one of these criteria. Okay? But on the other hand, augmenting greedy with look ahead gives you the ability to do better than you might otherwise do. Any questions? It also should be clear that you don't want to build the tree until every leaf is pure. If you build that, if you have n training examples, you've got a decision tree with n nodes in it. Okay? You've got n leaves, so you've got something like n internal nodes or n minus 1 internal nodes to get the n leaves. You're likely going to be getting something that's overfit. Okay? Generally speaking, you probably don't want to, keep splitting until one node has, no entropy in it. Okay? What you probably want to do is to keep splitting until the information gain of the next comparison is very small. Okay? If the information gain is relatively small, maybe you've done about as well as you can do with simple tests at this point. Okay? So basically, you don't want a tree with n nodes in it, okay, because it's going to overfit. The basic strategies are: 1, stop dividing when you stop making progress. or alternately, you could kind of build the full decision tree and then look at what nodes had the lowest value, okay, and eliminate them. Again, building decision trees is a lot of fun. It's a good computer sciencey thing. It's a good hacking-y thing as opposed to a mathy thing, okay? But, so there's a lot of different ways you could, decisions you could make that you have to evaluate and things like that. Any questions? So the good thing is that that we can build using these kind of techniques, given a set of decision trees, given a set of elements, we can build a decision tree on it. One thing I guess I didn't talk about is, if I'm building a decision tree, how do I decide what feature I use at every node in the decision tree? Okay? I described that once you have a feature, you have basically a threshold test you want to do. And I said that the information gain criteria is a good way to decide what threshold to use. But if you have a world where you've got 100 features here, which feature should you choose next? Okay, so you could do many things. And one thing, possibility, the simplest thing might be try all features, try the information gain for all possible features, okay? And pick the feature that has the best information gain, okay? So you could certainly try all the features as candidates for this slot, and then try all possible thresholds for the candidate in that slot. Find the thing that had the best information gain and use that. That's one approach. Another approach that turns out to be pretty good and has certain other advantages is to randomly pick which feature you use in a node. Okay? The good thing about picking randomly is that you can build many, many, many different decision trees. If I insist on a greedy approach where I always pick the absolute best split at every given point with the absolute best feature, there is only one tree like that. If, on the other hand, I pick a random feature and then find the best threshold, and then pick the best feature, a random feature, and best threshold, I can construct hundreds, thousands, millions of different decision trees, because the subsets available at every node depend upon what was the path above it, okay? The advantage of creating an ensemble of many decision trees is this gives us a chance to kind of come up with more robust classifiers and also get a better idea of how much to trust our classifier, okay? If, let's say, I build 100 random decision trees and I find that 75 of them say the kid's going to survive, and 25 of them, if I built, I guess 100, I said 1,000. If I built 1,000 of these trees, if 750 of them said the kid's going to survive and 250 of them say the kid's going to die, then I know, first of all, the kid's going to survive, and my confidence level, that's a label I'm going to give. And the confidence about this is that I'm probably going to be wrong, maybe 25% of the time. It gives a natural interpretation of how much should I trust that thing. So voting lets us use multiple trees. It gives us a sense of robustness, okay? That we're not, we're not making the decision based on just a small number of feature tests, okay? And it lets us see how much of a consensus is there among those trees, which gives us a measure of confidence. Any questions about that? What's the disadvantage of using multiple decision trees? The good thing I think you should see is that it's probably going to be more robust. I think people can accept that. People can probably accept that that you get that the margin by how much these trees agree with each other probably gives you a notion of confidence. Just like with nearest neighbors, if you 10 nearest neighbors were all male, the guy's male. If 7 nearest neighbors were male and 3 were female, you're less certain, right? What's a disadvantage of using multiple trees? It is computationally more expensive. You're spending more time at inference time. Maybe more time at construction time too, but I think that the bigger cost is probably at the time that you're running it. Okay? Any questions about that? There are other ideas that you can use to try to select different, make sure that you get more than one tree. Remember, we had this idea that maybe the best single tree would be one that would use the feature and the threshold at each node that did the best possible partitioning. One way we can salvage that idea is with an idea called bagging. Bagging says instead of training the tree on the full set of items on each time, maybe pick a subset of items. Okay, 25% of the items, 10% of the items. I don't know what you want to do. Come up with the best tree you can on those items. And then do this with a lot of different subsets. Now again, you get the idea where you've got many different trees, so you can vote. Okay? All these trees are semi kind of, not completely dependent on each other. They looked at different elements, but they did as good as possible a job of building the trees. Okay? Bottom line is there's different ways you can get many decision trees. Okay? And then vote among them. Any questions? Now, if you have, let's say you have 1,000 decision trees at the end, should you give all those trees equal votes when you're trying to elaborate this? Okay? One possibility is if I want to know the right answer to something, I ask every person in the class, is this, I can say, is this thing red or, is my shirt red or green? I ask everybody in the class, 90% of you say that this is red, 10% of you said it was green. Okay, one possibility is I let majority rule. Okay, are there other possibilities for considering those votes? Or is, if I wanted to, let's say, think about how I should aggregate the data from those decision trees. Okay? Is giving each one an equal vote the only thing I can do? Or is there some other strategy? Well, I think what either I'm going to give every tree it's an equal vote, or I'm not going to give each tree an equal vote. What would be my criteria for deciding whether to give one tree a bigger vote than the other? Okay? Accuracy seems like a good first try, right? I could take my decision tree, I could run it through all the training examples, okay? Or if you want if I have, let's say, testing and validation, if I have extra sets, I could see how good a job does each tree do in classifying it, and give more weight to the ones that are more accurate. That would be another trick that I could use, okay? The interesting thing is that doesn't always do quite what I want it to do, okay? Let's take a look at, again, a natural thing to do if I have a lot of trees At first I should give the first natural thing is, basically give each classifier an equal vote. A second idea is that I might want to weigh certain classifiers more than other classifiers, okay, based on how good they are. So look at an example here. Here we have a world where there are 5 different classifiers. These are the items. These are the classifiers. They're V for voters, right? One possibility is to take a look at every voter, said, look, on these 5 items, this voter got 4 of them right. He was betting 80%. On this one, okay, the voter was getting 3 right. That was 60%. In fact, all the other voters all got 60%. Does everybody see what's happening? Now, what if we take the majority of classifiers, okay? If we say that the star means that they got it right, okay, and the blank didn't mean it. The majority of ones, okay, if we take what most of the classifiers decided, okay, we would get 3 of the, in this example, we would get these 3 items correct, because here 4 items of the voters had the right answer. Here 4 of the voters had the right answer. 4 of the voters had the right answer. On these other 2 items, only 2 voters had the answer. Does everybody see on this particular example? Okay. We have we have a world where the best voter got 80%. The majority only got 60%. Right? That's if we were voting them equally. The other possibility might be that we weigh the votes more heavily for the guy that got it right. That would be the approach we were talking about a moment ago. Maybe we would count this guy as twice right, okay, and the other guys all got 1 vote. That would be a way of rewarding the top guy. But note that the top guy got something wrong, okay? And if we weigh the top guy heavily, we're still not going to get 100% on this test. What is the right way to weigh these guys? It turns out that if you give each of these first three voters, let me clear this a little bit. If we give each of the first 3 voters a 1/3 property, okay, then in fact, so we will let's say let these 3 people vote and ignore the last 2. Does everybody see that we get the majority right on every single item? We would get 100%, okay? Now, why did we decide to weigh these guys who got 60% accuracy, but not these 2 guys who also got 60% accuracy? You see that there's a little problem here? We like these. It should be clear that if we weigh all 3 of these items, if we take only these 3 voters, we get 100%. What is the difference between these 2 voters and these 2 voters? These guys got the hard ones correct. That's sort of the interesting property about these 2 voters. These 2 voters got the hard examples right, even though they were pretty dumb when it came to the easy examples, right? Really, in some sense, you would like to be able to, if you want to combine the voters, one strategy is to look to see, say, I want voters that are getting right the things that I'm getting wrong, right? If we think about, do you want a diversity of opinion? If everybody agrees on everything, having 100 people vote is no different than having one dictator, right? If there is some group of people who have contrarian opinions that are sometimes right and in fact get the hard things right, those are valuable people, okay? And if you follow that line of reasoning, that gets us into the idea of a technique called boosting. Boosting is an idea for how do you combine large numbers of weak classifiers, okay? They do better than random guessing. If they do worse than random guessing, you don't want them here, okay, at all. But if they do, what if you have a lot of different classifiers, all of which do something, okay? How can you combine them to a strong classifier? The boosting idea is that we are going to, again, reward classifiers based on whether they get the hard examples right, okay? And to do that, what we're going to do is we're going to identify which elements are hard and reward you for getting the hard ones right, okay? That's kind of the idea behind boosting. So what is the boosting idea? Okay, again, there's many different variants of boosting algorithms. The eta boost algorithm is going to start out by saying we have a world where here we've got positive examples and negative examples. It turns out that the best separator between these two is a nonlinear thing, okay? If we use threshold classifiers, we're either going to have horizontal chops or vertical chops. How can we find this nonlinear boundary from all of these things? We're going to start out by assuming that all the points have equal weight, okay? And then find what is the best single classifier, the single accurate classifier that does the best job of splitting it. Let's say that that was over here. This was our best single split. What are we going to note? It got some points correct, positive, some negative points correct. It had some points that were negative, that were positive points in the region we labeled negative, okay? These points we're now going to consider in the next round more important, okay? When we score the accuracy of our classifier. If we get this one right, we get 1 point. If we get these right, we get more than 1 point, okay? And the boosting idea is basically going to have a classifier and assign each point a weight according to the following kind of thing, okay? The weight of each point in the next round is going to be the weight in its previous round times some factor, okay, which is proportional to whether we got it right, okay? That's really kind of the important thing, the accuracy, okay? It's the accuracy of the previous classifier and whether we got it right, okay? And based on this, the points we got wrong will get higher. The points that we got right will stay the same. If some of the points have higher weight and some of the other points stay the same, the total weights of the points are going to be now greater than 1. If originally we gave each point a weight of 1 over n. So we normalize it down. Bottom line is, at each iteration, the value of points is going to change. And we're now going to seek the next classifier that will be most accurate at the weighted identification of the points that we have here. and we add that to the ensemble. So what is the basic idea of the eta boost algorithm? Again, we're going to want one that we want to find the, in each round, we're going to find what is the learner that minimizes the weighted error of the misclassified points. We're going to give that classifier a weight based on how accurate it was. Okay? If the best classifier didn't do a good job, we don't want to give it a high weight. If the best classifier did a good job, we want to give it a high weight. We're going to add that to the ensemble. Then we are going to adjust each of the points, where the ones that were misclassified are going to go up in weight. The ones that are going to go down, that were classified right, will, when we renormalize it, go down. Okay? Any questions? And again, the math is done to yield a result. Okay, that there's some theoretical bounds that you will get. Okay, but the intuition here should be good. With each one of these classifiers, you're going to be getting a weight associated with it. Okay? Now, for every point, when you have a query point, you're going to test which side of the line is it going to go on. And we're going to weight the confidence of our decision based on how good the classifier was. Okay? And each point is then going to get the label, okay, assigned by the weighted regions of it. So the one where the weighted region is highest. Okay? And this is the boosting algorithm. Okay? It gives you a principled way to make sure that you classify all that eventually you're going to have a classifier that could classify every single point correctly. Okay? The good thing is you can use a lot of different classifiers and combine them. The good thing is you will eventually get every one of your test cases right. That's a good thing. The bad thing is that boosting is going to work really hard to try to fit an example. Make sure it gets every example right. If you've got something that absolutely, by all of its properties, should be in class 1, but for some reason is labeled in class 2, it's going to go really hard out of its way to get that item right. Okay? And this has the property that if your data is noisy, there's a chance that this is going to overfit. Okay? It probably, this is the kind of big risk that you kind of get here. There's a saying in the law that when you have a hard case, one where the judge really has to think about it, that really kind of it looks like it's an exception, this is a bad thing to generalize from. Okay? And that's the problem when you do boosting on noisy data. That said, if you look at Kaggle competitions, and afterwards they interview the winner and say what was the machine learning method they used, the winner usually ends up using gradient boosted decision trees, okay, as kind of a method. Any questions about it? So decision trees and boosting are a good idea. Okay, any questions on these techniques? If not, thanks for your attention. Have a good Thanksgiving, and may the final project report be part of your holiday. Okay? Any questions about that? Okay, thank you very much.